Hey everybody, and welcome to our first lecture video on probability theory. We're finally here. So I want to begin this video by first just briefly recapping where we're at in the course, as we often do at the start of each week. So we're looking at inductive logic, that is the study of proper inference, where propriety or the goodness of inferences is understood in terms of inductive strength. An argument's inference, its move from its premises to its conclusion, is better or worse insofar as the premises of the argument render the conclusion probable. We said that a key task for inductive logic was to make this notion of inductive strength or inductive probability more precise and to formulate a method for assessing the inductive probability of arguments. We called this the task of constructing a scientific inductive logic. In week 2, David Hume challenged us to rationally justify the use of such a logic, while Nelson Goodman taught us that even constructing, let alone justifying such a system of logic would be challenging, given stuff like the Grue paradox. These challenges, while not decisive, motivated us to consider Hume's suggestion that maybe we'd be fine just basing our judgments of inductive strength off of our instinctual tendencies. No scientific inductive logic needed, right? That was the thought. Well, hopefully in week 3, the findings of empirical psychology and behavioral economics convinced us that the heuristics we often employ in formulating probabilistic judgments can lead to biases or systematic errors like base rate neglect or the gambler's fallacy and so on. So there's need to think a bit more rigorously about constructing a scientific inductive logic. Last week we started this positive project informally, but hopefully practically, by examining good forecasting practices like Fermiizing, estimation problems, or approaching questions from different angles or viewpoints, taking inside and outside views. Hopefully practices that can help correct for some of the biases we looked at in week 3 when it comes to making judgments about inductive probability. This week we're going to be constructing a more formal or mathematical approach to understanding inductive probability. We're largely going to leave discussing the interpretation and justification of the principles of probability for a future week. But what we're going to focus on this week is getting some of those basic principles on the table. Okay? So that's what we'll talk about today. So recall that the two notions of probability we've introduced so far in this course are inductive probability, right, and epistemic probability. Epistemic. Now recall that the main difference between these two notions was that inductive probability applies to arguments, right? We assign inductive probabilities to arguments, and epistemic probability applies to statements or propositions. All right? So the inductive probability of an argument is the probability of that its conclusion would be true given that its premises are true. And the epistemic probability is just how likely the epistemic probability of a statement is just how likely the statement is to be true. We said earlier in the course how we could understand epistemic probability in terms of inductive probability. It's also possible to understand inductive probability in terms of epistemic probability, and we'll see that when we discuss conditional probability. It's arguably a little less satisfying philosophically, though it's very common mathematically. And there's something of a debate, actually, in philosophy, or at least a discussion about which is more basic, inductive probability or epistemic probability. And we'll see some of those issues in future videos. For this video, I'm just going to focus in terms of epistemic probability. Although everything we say about the basic mathematics of probability would be statable in terms of inductive probability as well, albeit perhaps a little more clumsily. So for the sake of simplicity and straightforwardness, I'll speak in terms of epistemic probability in this video. Okay, so probability in general then, right, is a numerical measure of likelihood, right? Right. Propositions are assigned numbers that indicate how likely they are, right? So what does this mean? This means basically that, right, if x and y are two propositions we have, then the probability of x is going to be bigger than the probability of y, just in case, right, x is more probable than y. Right? And they're going to be equal. The probability of x will be equal to the probability of y, just in case x and y are equally likely. Okay? So what we have then is, right, probability is really a function defined on statements, right? A numerical function defined on statements. So if we want to think about this really precisely, right, we could say, right, suppose we have a set of simple statements, let's call it S, right? So S is a set that includes simple statements, so statements that don't include and or and not, right? So S is a set of simple statements. Okay, now let's consider an enlargement of the set S, under which we close it under the standard logical operations that we're familiar with, and, or, and not. So I'm going to write that enlarged set as A parentheses S, right? And we could refer to it as the logical algebra generated by S. Okay? This is some technical jargon, but hopefully through example the ideas won't be too bad. Stop here and think about an example. So maybe we could have a case where, right, S is equal to P and Q, right? These are represent the two simple statements we're considering. And A of S in this case would be equal to, it would include S, so it would include P and Q, but it would also have all the statements we can form using just P, Q, and the logical connectives that we're familiar with, and, or, and not. So stuff like P and Q, right? And not P, right? And P or Q, and not P or Q, right? And various other things we could do, right? P and Q, or not Q, right? So on, right? There's going to be a lot of different ways you could write things here, right? So this AS is just an enlargement of S that includes all the different propositions or all the different statements we can form just using the simple statements that are in S and our logical connectives of and, or, not. So it's going to be a lot of different things, right? Now, probabilities, we're usually going to be interested in assigning to the members of a set like AS, right? That is, we're not just going to assign probabilities to simple statements, but also to all the different logically complex statements we can build out of those simple statements, okay? So a probability function, right? A probability function P is really a function from a set like A of S to the real numbers, right? The real numbers are all the numbers that are represented on the real number line, right? So in general, this is what a probability function is, right? We're assigning numbers to different propositions, both logically simple and logically complex ones. And the higher the number, the more likely we're saying the statement is. The lower the number, the less likely we're saying the statement is, okay? Now, probability theory and inductive logic are concerned with putting constraints on what probabilities we should assign to different statements, right? And the way probability theory goes about doing this is in the first place through some basic axioms or constraints we put on the legitimacy of numerical measures of likelihood. Those constraints we call axioms, right? An axiom is just a basic principle of a theory. It's a starting point or assumption for a theory on which we build everything else. So in probability theory, we have three basic axioms, or at least when we're just dealing with unconditional probabilities, we have three basic axioms. When we introduce conditional probability next week, we'll add a fourth axiom. in basic unconditional probability theory, we have three axioms. Those three axioms are often called the Kolmogorov axioms. Named for the famous 20th century mathematician Kolmogorov. So these are constraints on what gets to count as a probability function. We're going to say that not just any assignment of numbers to a set of statements is going to get to qualify as a probability function. Only ones that satisfy the following axioms. Okay? The first axioms, and you should know these axioms, all the exams and everything are open notes, so you'll be able to look at these axioms when you're solving problems from your, for exams using your notes and such. But it's really handy to know them and to have a real ease or familiarity with them. So I would really acquaint yourself with these axioms and with the rules that follow from these axioms, which we'll derive in the upcoming videos. So the first axiom that we want to know is what's called non-negativity. According to non-negativity, the probability of any statement has to be a non-negative number. So in other words, we're restricting our probability functions. We're saying that probability functions can only assign positive real numbers, right? So the probability of any statement x has to be greater than or equal to 0. It can't be a negative number. Right? This is for all statements x. Okay. Now this is to some extent conventional. The extent to which it's conventional is something we won't really discuss much in this class, though. It will just be something that we know or assume is the case going throughout the course. So that means, right, anytime you're asked to give a numerical probability on a homework problem or an exam problem, should never give a negative number. Always give a positive number. Okay. Now, suppose that we want to assign probabilities to statements. We now know that they have to be positive numbers. Right? There's some further questions we might ask. So an initial one that might come to you is, should there be any maximal probabilities? Right? That is, are there any statements that we assign maximal probability to? So should our probability functions be bounded? Right? And very plausibly, the answer is yes. Right? There's plausibly a class of statements that appear to be maximally probable. And those are the class of tautologies, right? You may remember from our video on truth tables and propositional logic all the way back in week 1, we talked about the notion of a tautology, right? So it's going to be helpful for us to recall that notion quickly. So recall what a tautology is. A tautology is a proposition that has to be true just in virtue of the meanings of the words and, or, and not, right? So in other words, it's a statement that has only truths in its column of a truth table. So an example would be something like P or not P, right? If we drew a truth table and we made a column for P or not P, and we looked at that column, we would see that in every row it has a T or a true associated with it. That means that this proposition is going to be true no matter what the truth value of its individual component, P or not P, are, right? So this makes it a tautology. Now, tautologies, since they have to be true, right? They're true no matter what, they plausibly have maximal probability to them, right? And this motivates the second axiom of probability theory, what we call the Normality Axiom. And according to this axiom, any proposition that's a tautology should get assigned probability 1. Now, the choice of 1 here is also arguably conventional to an extent, although, again, the extent to which it's conventional we won't discuss in this class so much. But what we're really doing here is we're fixing a sort of maximal probability, right? We're saying the probability of any tautology is going to be 1, and so that's fixing 1 as sort of the greatest probability that any proposition can have. So now that means, given putting non-negativity and normality together, and as also in light of the axiom we'll introduce shortly, this is going to end up meaning that all of the probabilities that we ever assign to any statement are going to be numbers between 0 and 1, right? So on any exam, any homework, when you're asked to give a numerical probability, you always want to give a number between 0 and 1, right? If you're giving a negative number or a number like 1.5 or 30 or any number that's outside the interval 0 to 1, you know it can't be right? You've got to go back and check your calculations again because it would violate the axioms. Okay, so we said that tautologies always get probability 1, so that tells us how to assign probabilities to some statements, but it's a very limited class of statements, right? What about logical contingencies, right? Those propositions that are sometimes true and sometimes false. Well, the probability calculus doesn't tell us how probable the different rows of a truth table are, right? Which is a problem for inductive logic, right? We want to say how probable any different statement is. But it's not one that's directly going to be solved by the probability calculus. What the calculus does tell us is that the assignment of probabilities that we give to statements is constrained by our assignment of probabilities to logically related propositions. And the main constraint that we impose is this third axiom, which we call additivity. And according to this proposition, the probability of a disjunction of two mutually exclusive propositions, A and B, is equal to the sum of the probabilities of the disjuncts, probability of A plus probability of B. If A and B are mutually exclusive. Now, mutual exclusivity is a notion that we can understand in terms of truth tables. And I'll highlight this because it's important to note that this axiom is not true for an arbitrary A and B. It's only true when A and B are mutually exclusive. Intuitively, the idea of mutual exclusivity is that two propositions are mutually exclusive when they can't both be true, right? It's impossible for both A and B to be true, right? So if we want to think in terms of truth tables, right, A and B would be mutually exclusive just in case there's no row of the truth table in which both A and B come out as true. So here an example would be mutually exclusive. We'll say, I'll write out the definition first. Two propositions A and B are mutually exclusive just in case they can't both be true. That is, their conjunction, A and B, is a contradiction, right? That is, if we were to draw a truth table, right, we could test to see if A and B are mutually exclusive by looking at the column for A and B and making sure that it's a contradiction. That is, making sure that it has only falses in its column of the truth table. Okay, so now we have our three axioms. Let me actually put them all together here. Okay, so now let's review. So we have three key probability axioms. Non-negativity, which says every statement we assign a probability to has to get a non-negative number assigned to it. Second, normality, which says that every proposition is a tautology. That's every proposition that if we were to put it in a truth table, every row in its column of the truth table would have a true there. Every tautology has to get probability 1. Note that this is not saying that every proposition that has probability 1 is a tautology. It's just saying that every tautology has probability 1. So being a tautology is sufficient but not necessary for getting probability 1. And then we have additivity, that the probability of a disjunction of two mutually exclusive propositions is equal to the sum of their probabilities individually. Okay? So this is a fairly simple set of just three axioms. And it's amazing that we'll be able to derive a lot of handy probability rules from just these three axioms that'll allow us to answer some interesting questions in inductive logic. Okay, so in this video we've gone over the basic axioms that govern the mathematics of probability. In the next video we'll start to look at how we can use these axioms to derive some basic rules that will help us to identify the probabilities of more propositions. And we'll also work through some more examples that'll be similar to things that you'll have on homework and exams. All right, so please complete the participation poll for this video, and I'll see you in the next video. Thanks.